So is there anyone else who has a homework? Okay. Now, so this is the first time, but typically when I start teaching, I do not accept homework anymore. Let's get started. We are finally done with the mechanics of materials packet. We are going to start with failure and fracture mechanics. And today, hopefully, we are going to do this packet on failure. You see the chapter in the textbook and the other reference that it is in your syllabus for more details to go to. Now, I guess the first thing we want to do is to ask ourselves, why do we care about failure? The picture to the right, I guess we have seen it many times before, and you probably were too small to remember. I was living in New Jersey back then, and we could see the smoke from where we were. And this is the World Trade Center. A failure. From a structural side, it was when the fire started, the steel in the building gets very hot. It loses yield strength, and then it fails. So from a structural point of view, that's a failure because of fire. And of course, I mean, it is a failure in many respects. I don't know if you have visited the memorial. I definitely encourage you to do that. How many of you have visited the memorial? That's great. I really encourage you to do that. How about the one to the left? Does anyone recognize that? You are all too young even for that, I guess. Anyone? It's a collapse of a bridge on a major highway. This happened in Minnesota. A gusset plate failed, and it was during the day. There were cars, and they actually went to the river. Afterwards, there was a big surge in researching the gusset plate and the fatigue behavior of steel. So I guess even showing you two examples of failure is enough to realize why we need to study failure. We are studying failure because we don't like it, because people lose their lives, and because we have a lot of costs and interruptions to public. So what is failure? If you want to define it, any type of inability to function, the intended function, is failure. This can mean different things in different contexts. For example, it can be excessive deformation. And one thing that we have talked about can be just yield. If the stress passes the yield strength, the material it has a lot of deformation, and then you have excessive deformation, plastic, and you have failure. There are some other things here that we want to focus on today. For example, fatigue. Maybe you are familiar with it in everyday life. For example, today you've been in too many classes. So if you have a lot of different classes, then it is hard to sit in a class for 50 minutes until 30 p.m. So you are fatigued, right? So it happens when you have repeated loading. Going back to the running, if you go running once in a while for 6 miles, you may be fine. But if you do it every day, maybe after 3 weeks, you cannot walk down the stairs. Speaking from experience. So you may have fatigue just because you repeat the loading The loading may not be as high to cause yielding, but if you repeat the same thing over time, you may experience fatigue. Okay, so we want to talk a little bit more about these concepts here. After any major failure, forensic teams go back to the failure site and try to find out why failure has happened. And typically, there is a problem and the codes were not followed. This is easy to fix. Good engineers can make sure that you will stick to the specifications and this doesn't happen. But sometimes the theory was available, but it was not yet found its way to the code. And in some other times, which becomes more rare and rare, because we are learning more and more about materials, we even don't know why the failure happened, and that intrigues a lot of new research to find out what's going on. So, if the material is ductile, if you have this kind of a stress-strain behavior, where you have a lot of deformation before failure, you can use this method of strength of materials, something that you may be familiar with. Typically, what we say is that, okay, here we have ultimate strength. We talked about this last time, the maximum on this load. And here you have yield strength. That is when afterwards the material behaves plastically. It's not reversible anymore. And we can use something like that just to make sure that the material doesn't fail. And the way we do it in a strength of materials is this. We say, okay, as long as we ensure the stress is less than the strength. Now this can be ultimate strength, it can be yield strength, etc. As long as a stress is less than a strength, we are going to be okay. So here is a stress, here is a strength. Logically, if the stress is less than the strength, we are going to be okay. But we typically divide this strength by something which is called a safety factor, or sometimes you hear factor of safety. The same thing. Why do we need to do that? Why do we not just go with a stress less than a strength? Yes?
You have to account for the uncertainty in the material.
Exactly. We said that civil engineering materials are very variable. And if we do that, we say, okay, a stress is less than a strength, everything is going to be okay. The reality is we have uncertainty both on material side and on the stress side. You may design a bridge for 10,000 truckloads, but then there is any routing and you get 11,000. You don't want your bridge to fail. At the same time, the specs for the steel says a strength is this much, but there is variability. So maybe that what is delivered to you doesn't have exactly the same ultimate strength. So now, from a statistics, you know that, for example, you can look at the normal distribution. What you want to make sure is that your stress is less than a strength. You are in this area. And because of that, you account for these variabilities by dividing the strength by the safety factor. Now, today, I want to convince you that this approach by itself is not enough. It can, your structure, your bridge, your high-rise can still fail. And we want to learn why is that. Let's do one small example here to make sure that you understand this procedure. So here is the basic formula. Here we are looking at a plain concrete, very simple beam, which sustains one load in the middle. And it is a bending. You have seen it in structures or in strengths of materials. It is called this kind of bending. It's called three-point bending. And you will see later that this is being used to find the tensile strengths of concrete, which is sometimes also called modulus of rupture. So this is a strength. And it is tensile strength. Okay. If you use a safety factor of 3, the question is, what is the maximum load you can apply on this beam? So, what would be the maximum load to make sure that this beam does not fail? We use the term fail. Fail by considering that a stress has to be less than a strength. So you need to calculate the maximum tensile stress, and you have to make sure that it is less than the tensile strength divided by this safety factor, which is 3. Now, if you forgot how to calculate the tensile strength, it is maximum moment times half of the height divided by moment of inertia, and you get a relationship between tensile stress and the force. So go ahead, work with the neighbors, and try to see if you can calculate the maximum load just using this simple approach. A stress less than a strength divided by safety factor. So this U here is kind of stands for ultimate. Here the concept is important. The stress has to be less than the strength divided by safety factor. Now in this case it's the tensile stress, so we want to make sure the maximum stress in the beam is less than the strength divided by safety factor, which is 3. So please work together, make sure you understand what's going on, and let me see a few correct answers. Make it larger. Okay. Thank you for asking. I never know. I don't know why today two slides went in one page. Make sure this is have an idea why. Let's also check that where the quizzes are. Did everyone got this graded or they're graded this way? No? And then the attendance sheet. Did everyone sign? So what happened? It's never got here. Attendance? It's here. Okay. It can go slowly. I just want to make sure that everyone knows that the graded quiz is circulating. So let me see, I need to see 3 correct answers. Don't forget the safety factor. If you just use 5, that means that you don't take into account any variability, no safety factor. You need to see 3 correct answers. Did you guys see this? Anyone here who did not sign? Anyone who thinks she or he has the correct answer? Stress, the maximum stress, tensile stress, has to be equal to tensile strength, which is 5 megapascal, divided by safety factor. Now, I gave you how to calculate this tensile stress, because in case you forgot. No correct answers? Okay. Well, so you want the stress in service, which is the maximum stress, and that's just what comes from the relationship between force in the middle and the stress, maximum stress, to be less than 5/3. If you just say 5, that means you are not taking into account the variability. That's a no-no. And you substitute. Now, I saw that in the other session too. People would use sigma is equal to P/A. This does not hold when you don't have normal stress. This is a tensile stress due to bending. And you cannot just divide this by A. It is the bending moment times half of the height over the moment of inertia of the cross-section. Because it's not normal stress. So this is nicer written. So here is the stress. And here is the strength divided by safety factor. And if you do the calculations, you see that the maximum load you can put in the middle of this beam so that you don't exceed the strength with a safety factor of 3 is about 7,000 newton. make sure this is all big enough. Okay. So this is the way we would design if we don't know anything else. If we only consider that the failure mode is reaching the ultimate strength, or it is the yield. I want to convince you today that this is not sufficient. So that's why we have to understand a lot more. Why it's not sufficient? Because experience has shown that a lot of times we have failures where a stress is much smaller than a strength. And if you want to account for that, you have to put safety factor of 10, which makes everything non-canonical. It will cost a lot if you want to over-design everything by a factor of 10. One good example of that is fatigue failure. So what happened in Minnesota was not because the stress was greater than the strength divided by safety factor. It turned out that it was not the case. The problem is something which is called fatigue. And it happens when you load, in this case, a gusset plate was where everything started. When the structure is under repeated loading, and bridges are by definition subjected to repeated loading structures. Okay. And the worst case scenario is when you have positive and negative load. So it goes through tension, compression. That's when you have fatigue happening the easiest. And what happens is a small crack develops, very tiny. Bridge inspector would not be able to see because it's beyond our vision ability to see those. And very slowly, this small macro crack propagates. At some point, it propagates very fast and quick. So towards the end, it is almost brittle. And if it is not being caught, you have this kind of failure. Now, what do we do about that? Well, it turns out that this is a phenomenon we know, so we can take care of it. Now we are looking at blue is steel and red is aluminum. Let me take these points off. So in the lab, you take a piece of steel, just like the example, you apply, for example, 3-point bending. So you apply a force in the middle and you use cyclic loading. Many cycles. Look here, the numbers 10 to the 4, 10 to the 5, this is logarithmic, 10 to the 6. And then you measure when it fails. So then you get these points. You repeat this many times and you obtain the fatigue characteristic. So for example, this piece of steel, if you look at this point here, if you have a lot of load, repeated loading at 40 KSI, it can sustain up to 5 times 10 to the power of 4 repetitions. Afterwards, it will break. That's what it means. Now, if you look at 35, somewhere here, so if you apply 35 KSI, it can go on for more cycles, but then it fails at that many cycles, which is about 2 times 10 to the 5. The nice thing about a skin is that after a while, if the stress, after a a while, no matter how many times you repeat, it's going to fail at 30, for example. So it's not going to go continuously down. And this is called the fatigue limit. So if you are concerned, for example, about fatigue for your design, you want to make sure that your stress is well below this 30. So no matter how many trucks are going over your bridge, the steel is not going to fail. Aluminum, on the other hand, here is, you see that with the number of repetition, the strength is just decreasing. That's why you don't see too many aluminum bridges. And let's say if I have a point, I tell you that I have an application where I know that during the lifetime there will be 2 times 10 to the power of 6 at 40 KSI. So there will be load about 40 KSI, and there will be 2 times 10 to the power of 6 trucks repetition. Which material do you think is suitable for my application? This is the kind of questions which I like to ask. So which of the 2 materials you think is appropriate for this application? Again, I haven't been still, I want to make it out of some material, I don't know what. But I know that because of the truck passing, I'll have 2 times 10 to the 6 trucks. And each one of them makes 40 KSI. So I'm going to have this repetition of 40 KSI, 2 times 10 to the 6 times. Which material should I choose? Neither. It will fail. If I choose a steel, it's going to fail at 30. Aluminum even worse. So neither is good. Right? If I had an application which was at 25 KSI and 10 to the 7, what material would be a good material for that application? Only a steel. Aluminum would fail at 20. So I would not be able to apply 25, not those many cycles. Or you can think of, if I use aluminum, it would fail at this many cycles. It wouldn't get to what I want to have. So just that you see what I mean. So this is again these 2 graphs. That was a real experimental graph. These are more schematic. So you can see I put unsafe and safe. I hope this is clear. So if you have a point, like for every application, you know what will be the stress and how many repetitions. If your point falls above the graph, it's unsafe. If it is below, it's safe. Yeah. You saw why. So it's a nice thing. We understand fatigue, and we have to take this into account. We can't just say stress less than the strength divided by safety factor, because you may have fatigue. So it's unsafe, safe, unsafe, safe. Now, I have more reasons to tell you why this approach, the beginning approach, is not good. Because sometimes we don't even understand the phenomena. Remember in the very beginning, I was telling you that this stress is less than ultimate strength divided by safety factor is good for ductile materials. It's not good for brittle materials because it's not very well defined where their strength is, and they can snap very abruptly. Now, is anyone from Boston? Any connection? Many years ago in Boston, in 1999, there was something called molasses flood. So it's kind of very scary. Everyone knows what molasses is. Pecan pie. So what happened was a tank which was full of molasses broke, and molasses was spread in the street. People were caught by it and many died. You can imagine it's hard inside. It's very hard. It's very scary to imagine being inside a material which is very viscous. If you know what viscosity is, we'll talk about this later. You don't have to know, but so why this happened? This was made out of steel. It turned out that this type of steel was actually very brittle. They found later on a small fatigue crack that had spread. So there was a fatigue crack, and when you have fatigue, the ductile material behaves like a brittle material. And all of a sudden, there was this problem. And this is not the only scary example I have for you today. The other one relates to Liberty ships. These were during World War II. I don't know if this picture is clear, but some of these ships, they were broken in half. And they were also made of very high strength steel. So at that time, people were very confused what happened. And years later, they found out that this steel that they used is such that at lower temperatures, it becomes very brittle. So when the temperature was very low in water, it actually became very brittle, and then there were cracks, and this is happened. So the point here is that if the material behaves very brittle, just saying that this with a safety factor of 2 or 3 may not be sufficient. This is not all. Another problem with that formulation is that ultimate strength turns out to be size dependent. So what do you think? If from the same material I have a small specimen and a large structure, which one is the strongest? It's fusion. Smaller one or the bigger one? The bigger one? Intuitive. Smaller? Intuitive. Turns out that he's right. And it is not very intuitive for most people to think that, because we associate largeness, like if something is bigger in size, we associate that with higher strength. Many, many years ago, 500 years ago, Da Vinci, he did some experiments on wires. It's actually pretty cool. And he saw that the same wire, if it was longer, it broke sooner. It's good. Griffith, later on, with glass fibers, saw the same thing. So someone could generalize that and say if you have a larger size material, then you are going to get lower strength. And it looks strange, but it's even true for, let's say, concrete. If you look at the tensile strength of concrete and the size, you see that after a while it goes down. Very strange. And here is our example. So you see that these are real measurements. You see the tensile strength. If, for example, you increase the size of the beam, there is a tendency to go down. Why do you think this is happening? How come? Then it's more likely for it to fail at a lower strength. Yeah, this is a part of it. But here we are looking at really not variations between different samples, but just the effect of size. And if you have the same sample, if you shrink it, it seems that it becomes a stronger. And if you take the same material and you just make it, you get a smaller and a smaller sample of the same thing, you start to see higher and higher strength. I actually have to show you this other graph. You see how dramatic that is. Here the thickness is very small, but look at the variations in the strength. It's not like by a factor of 1 or 2. It's by many orders of magnitude. What happens is that something along the lines of what your friend just said, when the material is larger, or when the spectrum is larger, it has higher potential to have flaws. And these flaws are macroscopic. You don't see them. So if you have a big, if it is very tiny, the probability of having a small flaw is much lower than when it is large. Why flaws matter? Because the failure starts from a flaw. A strength is different from a stress. So a strength is always looking for a weakest point. Some weakness inside the material. Just to show you these concepts, I brought this. I don't know if you are familiar with, I'm sure you are. So this kind of packaging, you may try to break it at some other location, right? And it's very hard. I don't know, sometimes if you've been on a plane, it happens to me, I cannot find where the little notch is and you cannot open it. It's very hard to open it. What do you normally look for? There is a little, very small, sometimes hard to see, kind of a notch. And the moment you apply just a little bit of force, so look here, this is the same material. I'm doing everything I can, I really cannot see it. But here, there is a little notch, very small. I apply a little bit of force, and it's broken. So if you have a small, tiny micro cracks inside, this is what happens. And the strength is not determined by this, because if it breaks from here, as you can see, you have access to the whatever is inside. I can actually pass this around. There are only a few somewhere. I don't know. If you're hungry. I actually looked for a larger package for everyone, but this was the only one with a perfect notch. In any case, what happens is that if you look inside the specimen, you have tiny little cracks, and it turns out that they control the strength. And the larger your specimen is, the larger is the probability of having these kinds of cracks. But the question is, why did it happen? Why, when I applied a little bit of force, why did it very easily, why I which is called a stress concentration. Now, look at this example. This is a very cool example. You have 3 bars in tension. If you look at the maximum stress, when we look at maximum stress here, this is normal stress, it's easy. It's just force divided by the minimum area, perpendicular to the force. If you look at these 3 cases, and let's consider a thickness of unity, just 1. We don't care. The maximum stress here is P over A, everywhere the same L. L times 1. Maybe it's better to write it L times 1. In the other one, the maximum stress happens at the minimum cross section. Is there a question? Okay. If there is a question, please ask. The maximum stress happens at the minimum area, and it's again E times L. But I write it L times 1 to make sure that we are not confused about that. And in the lower part, also the maximum stress is again E times L, E over L. The question is, which one do you think would fail sooner? They all have the same stress. So if I put a stress less than a strength, and this will be the maximum stress, they would be all equal. But it turns out that they fail very differently. Which one do you think will fail first, A, B, or C? B. Why B? Exactly. And then afterwards? Exactly. And then A. And because of the notch, so first is B, then is C, and then is A. Also, they all have the same stress. So a strength of materials method failed off, because it cannot know that. And the reason for that is when you apply the stress, if there was no hole or no notch, the stress would be uniform. When you have some sort of discontinuity in your material, it turns out that the stress is larger around that discontinuity. You can see that here the average stress is this much, but around the edges it's much larger, and this is called a stress concentration, and it happens near flaws. Now, why having a notch is worse than having a hole? It's because we will see this next time, that the sharper the edges are, the higher is the stress concentration. So it has something to do with how sharp the geometry is changing. If you have a hole, it's much better. So as a structural designer or as an architectural engineer, you want to avoid sharpness inside the structural membrane as a general rule, because that's where you will have a stress concentration, and that's where it becomes prone to problems. So it's the same thing. The strength of materials method doesn't consider that because it doesn't take into account the stress concentration. And because of that, you can have failure much lower. So it's important for us to actually find out where the flaws are. And I guess I told you that one of my research is on finding the flaws. without opening up the material. So it's very important to size the flaws and know where they are, because if we don't see them, they cause a stress concentration and then you have catastrophic failure. Now, and that's why we learn fracture mechanics. Now, kind of a very related thing to what we discussed is, I started by saying that ultimate strength is size dependent. And I hope I convinced you that this is the case. Now, it's important to discuss this for a second. What is a material property? So, a material property is typically something which is independent of size and shape. And we have a method to measure it. So, by that definition, a strength of material is not a material property because it depends on the size. Now, what do you think? Try to spend a few seconds on number 1 to 5 and decide whether these are material properties or not. Just put a check mark because you are tired. If they are, and just put a little cross. I thought it's important for you to realize that the material property always has to be independent of size and shape. And because of that, tensile strength isn't. It's size dependent. How about weight? Obvious one. No. Now, if you want to make weight a material property, what quantity do you use? What do we use instead of weight? Something which is a material property. Mass density. No, density. Mass is also depends on the size, right? Density. So now you see why people have defined this kind of. How about failure load? Is this a material property? No. It cannot be. How do we make this a material property? We can't really, because you saw that the strength is depending on the size. We cannot do that. How about elastic modulus? Perfect. Strain energy. What is a strain energy? Is the area underneath each here. That's the strain energy density. So you're right because you thought about the strain energy density probably. So a strain energy is under the area under force deformation. If you want to make it a material property, that's why people divide it by the volume and they call it a strain energy density. I don't know how much you had to do with the speed of light in a material. What do you think? It is a material property. The speed of light is inside every matter is a material property. Now it's Friday and I don't want to keep you to write this, but again, at the end of the packet, there are these points. I encourage you to take a look, make sure everything is clear, and there are these terms. Did everyone sign this sheet? No. I'm glad I asked. Did everyone give me his homework? Where? Is there anyone who didn't pick up his weekly quiz number 0 graded? So next time, please give it to me.
Mine? I thought you said my name.
No, I don't know. Did you pick up yours?
No, I didn't. I put my homework up here.
I think I took.
Okay, the bus driver just left the bus for like 15 minutes. So it was, I was like, she
then you
just
like
ran
already-
away and I was on the bus. So.
What happened? You too. Just walking into. Just walking into.